Hello everyone, welcome to my YouTube channel. This is Enoch's tutorial. Don't forget to like and subscribe to it after watching so that you can receive every update from this channel. In today's lesson, we are going to look at carboxylic acids and their derivatives. We will first look at the structure of the carboxylic acid functional group, then continue with IUPAC nomenclature of carboxylic acids with some examples. We will continue with the physical properties of carboxylic acids, including their boiling point, their solubilities, and also their acidities. Then end with carboxylic acid derivatives and how they are synthesized. Don't forget to like and subscribe to the channel after watching so you can receive every update from this channel. So let's continue. So carboxylic acids are basically a class of compounds in which a central carbon is bonded to an oxygen atom with a double bond, and also to a hydroxy group with a single bond, with a fourth bond linked to a side chain. So this is the structure of carboxylic acid. This is a central carbon here bonded to an oxygen atom with a double bond, a hydroxy group with a single bond, and a side chain here represented by R with also a single bond. This functional group is called a carboxyl functional group or a carboxylate system, and every compound that contains this functional group qualifies to be called a carboxylic acid. It has a structure that looks like an aldehyde or ketone, but just that here in case we have a hydroxy group bonded to the central carbon. Now let's look at the structure of the carboxylic acid functional group. Carboxylic acids have a central carbon here bonded to a side chain carbon we call an alpha carbon. So the carbon bonded to carboxylic acid in every compound is called an alpha carbon. This is the hydroxy group. This carbon here is called a carboxyl carbon, and this oxygen is called a carboxyl oxygen, We have an alpha carbon here. We have a hydroxy group. We have a carboxyl carbon and also a carboxyl oxygen. This whole complex constitutes the carboxylate system functional group. Without a side chain, this is the functional group of the carboxylic acid, and it defines the reactivity of carboxylic acids in every solution. Let's continue with some example. So this is an example of carboxylic acid. It has the carboxylate system bonded to a benzene ring. This also has a carboxylate system bonded to a cyclopropane ring. Other examples of carboxylic acids include formic acid, we have acetic acid, we have butyric acid, and also a benzoic acid. All these compounds have the carboxylate functional group present in them, so they all qualify to be called a carboxylic acid. So in other words, every compound that has this functional group present in them qualifies to be called a carboxylic acid. Let's look at the general IUPAC nomenclature of carboxylic acid as an organic compound. In general sense, organic compounds are all named based on the same principle. So just take the chain with the functional group as usual, then start the numbering from the functional group as shown here. Here's the carboxylic acid, so here we replace the corresponding alkene name with alkanoic acid. For example, if it is ethane, it becomes ethanoic acid. If it's propane, it becomes propanoic acid. So the last E of the corresponding alkene name is removed and replaced by OIC. So if it is, let's say, ethane, the last E is removed and is replaced with OIC to become ethanoic acid. Now you indicate the position of each of the substituents with the least possible number, and you arrange them in alphabetical order. We are going to look at some examples so we understand better. Now in case of cyclic carboxylic acid, you just have to write the name of the corresponding alkene and you just add carboxylic acid to the name. So let's look at some examples on how to name carboxylic acid. So example, here we have a chain with the carboxylic acid functional group. So this is the carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Here's carbon 6. So this is the longest chain that has the functional group in there. So we start naming or numbering from here. Then we indicate the positions of the substituent with the least possible number. We arrange them in alphabetical order. Then we replace the corresponding alkane name, the last E, with OIC. So here, if it was to be an alkene, it becomes a hexane because it is a 6-carbon compound. But here's carboxylic acid becomes hexanoic acid. In naming, we indicate the position of the substituent with the least possible number and arrange them in alphabetical order. So we have bromine here, we have methyl here. So B comes before M. So the position of the B is 4. So it becomes 4-bromo, 3-methyl hexanoic acid. 4-bromo, 3-methyl hexanoic acid. The bromo is B and the methyl is M. This is very important. You bring the one with the first alphabet first before the other, irrespective of the number. Now letters and numbers are splitted with a hyphen, whereas numbers and numbers are splitted with a comma. Keep that in mind. Letters and numbers are splitted with hyphen, whereas numbers and numbers are splitted with comma. So here, let's say you have 4 here, to become a comma in there. Let's look at some other examples. Here is the case of a cyclic carboxylic acid. So here, how to name it? Just name the corresponding alkene as a cyclohexane carboxylic acid. It is not cyclohexanoic acid, no. Cyclohexane carboxylic acid because it has 7 carbon. If you make it cyclohexanoic acid, you are trying to say it is made of 6 carbon, which is wrong. But here the case has 7 carbon, so it becomes cyclohexane carboxylic acid. The carboxylic acid here indicates the functional group here. Then the functional or the cyclohexane is the ring system. Let's continue. These are some examples of carboxylic acids with their name. So here it has 4 carbons. It becomes butanoic acid, or its common name is butyric acid. Here it has 3. The common name is propanoic acid or propionic acid. This is the common name. You have another one here, a pentanoic acid with methyl group on the 2nd carbon. So it becomes 2-methyl pentanoic acid. We have a propanoic acid with chlorine at position 3. So it becomes 3-chloropropanoic acid. The rest are their common names. Let's look at some other complex names. We have 2-methyl pentanoic acid, 4-isopropyl 5-oxohexanoic acid. So this is the isopropyl group and this is the oxo group. So a ketone on the main chain is named as oxo. So it becomes 4-isopropyl 5-oxohexanoic acid. 4-isopropyl 5-oxo. The oxo here, the OXO here, is the ketone functional group here. So 4-isopropyl 5-oxohexanoic acid. Here too we have I before O in alphabetical order. So isopropyl 5-oxohexanoic acid. We have methanoic acid, we have ethanoic acid, we have propanoic acid, we have 1-chloro 3-methyl cyclopentane carboxylic acid as shown here. So it becomes 1-chloro. This is the first carbon, this is the 2nd carbon. Here in this case, we don't start counting from this one because we don't class this as part of the parent chain here. So we name it 1-chloro 2-methyl cyclopentane carboxylic acid. Here in this case, the main carbon, the main chain is the cyclopentane. So we are trying to name all these as substituent. So it becomes 1-chloro, 2-methyl cyclopentane carboxylic acid. Let's look at some other forms of carboxylic acid. When carboxylic acid loses one hydrogen, it becomes what we call a carboxylate ion. When carboxylic acid loses one hydrogen, it becomes a carboxylate ion, mostly in an alkaline solution. So here it becomes sodium hexanoate. So here this group is called a hexanoate. If it was to be acid, it becomes hexanoic acid. If it loses one hydrogen, it becomes hexanoate. So sodium hexanoate is the name of this compound. Let's look at this one too. Here it has two carboxylic acids present. So it becomes ethane dioic acid. Ethane dioic acid, or commonly called oxalic acid. So it is ethane because it has 2 carbon. So ethane di means that it has 2 of the carboxylic acid. So ethane dioic acid. We have propane dioic acid. We have butane dioic acid. And these are their common names. You have oxalic acid, you have malonic acid, then succinic acid as their common names. Now let's look at the physical properties of carboxylic acids. The first thing you are going to look at is their boiling point, how they are able to boil, and what factors affect the boiling point of carboxylic acids. Now carboxylic acid can form hydrogen bonds with water molecules, and also they form what you call a dimer. So they form a hydrogen bond molecule pair. So the boiling point of carboxylic acid are higher than the corresponding alcohols of the same molecular or molar mass. So let's say we have ethanol and ethanoic acid. Carboxylic acids tend to form a dimer. A dimer is they form a pair. Now this pairing system increases the molecular weight by 2. So the boiling point, since it depends on the molecular weight, ethanoic acid and ethanol. Ethanoic acid will have a doubled molecular weight as compared to ethanol. In that case, the higher molecular weight leads to a higher boiling point. Now, because they can form a dimer and they assume a doubled molecular weight, carboxylic acids tend to have a very strong or higher boiling point than ethanol. Once again, because they form 2 hydrogen bond system, here the energy required to break that bonded system is very high as compared to that of the alcohol. So here it has 2 hydrogen bonded system even before the water molecule. So here it has a very strong hydrogen bonding system, which requires very higher heat or higher energy to break this bond before you can convert this one from a phase of liquid to the gaseous state, which defines the boiling point. So the stronger hydrogen bonding system confers a higher boiling point in ethanol or ethanoic acid than their corresponding alcohols. And also their degree of dimerization also increase their boiling point as compared to that of the corresponding alcohols. Once again, is their solubility in water. Solubilities are basically conferred by what you call the hydration energy, which is released after an interaction of the compound with oxygen, or let's say with water. If carboxylic acids interact with water, we need an energy which is going to be used to solubilize all the carboxylic acid in the aqueous solution, and that energy is called the hydration energy. Now, strong interactions with compounds or water molecules generate a very higher hydration energy, which can easily solubilize, or let's say mix or dissolve the compound in the aqueous solution. So carboxylic acid, which have very low molecular weight of 1 to about 4 carbon atoms, they are very soluble in water because their hydrophobic chain is very less, and that the interaction is going to be strong, and the hydration energy release is going to be high to be able to solubilize all the compounds in there to make it miscible in the water. So carboxylic acids with a very low molecular weight are soluble, or let's say miscible in water, whereas that which have higher molecular weight are partially or sparingly soluble in water. So formic acid, ethanoic acid, propanoic acid, and butanoic acid, these 4 are very soluble in water because their interaction with water molecules generate a very strong hydration energy, which can break down the bonds to make them soluble in the water. We are also going to look at the acidity of carboxylic acids. As the name implies, they are carboxylic acids, so they behave like acids. The OH group, or the hydrogen on the carboxylic acid here, defines the acidity of the carboxylic acid. So this, in an alkaline solution, the base can abstract this proton, and this one has the ability to lose this. So the ability to lose a proton defines your acidity. So since carboxylic acids can lose a proton in a solution, that's why we say they behave as acids and we call them carboxylic acid. When this one leaves, the remaining system is called the carboxylate system, or the carboxylate ion. Now, because they can lose this hydrogen to a base, or let's say a proton deficient species, we say they are acidic. Several factors affect the acidity of carboxylic acid. Two known of them are inductive effect and mesomeric effect, which we are going to look at in the next slide. So basically, you have these corresponding carboxylic acids. So you have this carboxylic ethanoic acid, chloroethanoic acid, dichloroethanoic acid, and trichloroethanoic acid. These ones have different degree of acidity because of what you call inductive effect. In the general sense, if there is a strong bond between this oxygen and this hydrogen, then this hydrogen can easily or hardly leave. Therefore, we say the compound is less acidic. If the bond here and here between this oxygen and this hydrogen is strong, or let's say it's weak, then this hydrogen can easily leave. Here we say it is strongly acidic or highly acidic. Let's look at these compounds here. If this is ethanoic acid with pKa of 4.8, the pKa stands for acid dissociation constant, which is proportional to pH. So higher pH means higher pKa, and higher pH means that less acidic. Lower pH means more acidic. So looking at these compounds, this one has a pKa of 4.8, pKa of 2.9, 1.3, and 0.9. So taking these four, this one has the least pH, in other words, least pKa. Therefore, this one is more acidic as compared to this. The definition is defined by what we call an inductive effect. The inductive effect is basically electron withdrawing or electron donating effect of a substituent. If groups like chlorine draws electron from the carboxylate system, they tend to weaken the bond between the O and the H. Therefore, a base can easily abstract the proton, making it more acidic. Chlorines tend to pull electron from this system. When they tend to weaken the bond between the O and the H. Now, the pull of electron from this system towards itself is what we call a negative induction. Negative induction that weakens the bond between the hydroxy group or the oxygen group here and the hydrogen. Therefore, a base can easily take the protons out. So here we have two strengths, one strength here, two strengths here, and three strengths here. So comparing this one and this, there is a high degree of negative induction in this compound than this. So we have a deficient electron here than this. So if electrons are deficient here, the bond between the oxygen and the hydrogen are going to be weak. So the hydrogen can easily lose. That defines a higher acidity. Now the position of the atoms also defines the pKa or the acidity. In this case, where the chlorine is at position 2 with the alpha carbon, here at beta carbon, here at gamma carbon, the negative induction conferred on this carboxylate system in this carbon is higher than that of this. This one too is higher than this because of their distance from the carboxylate system. This is the principle of induction. Other compounds, or let's say other substances like methyl groups, which are electron donating, tend to decrease acidity because they give electrons to the carboxylate system to strengthen the bond between the hydrogen and the hydroxy group here. Therefore, a base can hardly take out the hydrogen. That defines a less acidic compound. Let's look at some more examples here. We have acetic acid, we have chloroacetic acid, we have dichloroacetic acid, and trichloroacetic acid. So as we move here, we tend to increase acidity because of the negative inductive effect of the chlorine which tends to pull electron from each of these carboxylate system. Another principle we use to define or explain acidity is the principle of mesomerism or resonance. When a base takes a proton from this system, the resulting ion is called a conjugate base. Let's see if we had an example here. I think we had none. Yeah, so let's look at this compound. So this compound is a conjugate base. Now, conjugate base is formed whenever a base takes a hydrogen from a carboxylic acid. Now, when this one assumes an ionic form, there is a delocalization of electron between this oxygen and here. Now, the distribution of electrons between these oxygen atoms around the central carbon is what we call resonance, or what we call mesomerism. So resonance and mesomerism are synonymous. Now, if there is a possibility of you forming a very strong conjugate base, then we can easily lose a hydrogen atom. Therefore, compound that can form a very strong conjugate base, that is the one that has less electron here and can partially or delocalize electrons between the two oxygen atoms, have higher acidity. So, if you have electron withdrawing groups like as seen down here, these groups, they are going to make the electron system or the electron density of the carboxylic system very less, and that the resulting conjugate base is going to be strong, or let's say very stable. So when it is stable, it means that the acid can easily lose hydrogen to assume the more stable form. The delocalization of electrons between the two oxygens, this one and that one, is what you call the resonance or the mesomerism. If the resonance is very stable, then it means that the initial acid is a very strong acid. In other words, if the resonance is less stable, then the initial acid is a weak acid. The resonance becomes stable when there is a less electron density, and more stable when there is a less electron density here, and less stable when there's more electron density here. So what affects the resonance is also the electron pooling effect. So basically, inductive effect also has an effect on the mesomeric effect that defines the acidity of carboxylic acid. Let's look at these aromatic compounds here. So here we have a benzene ring here with carboxylic acid. Now, methoxy group is an electron donating group. They give electron to a system, therefore they will weaken or strengthen the bond between this oxygen and this hydrogen, therefore making it less acidic. So this one is less acidic as compared to this. A nitro group at a meta position is also less acidic than the one at the para position because of the stability nature of the resulting conjugate base. So the auto position nitro group is the more stable, or the one that has a more stable conjugate base, and that the more acidic, carboxylic acid. So let's look at carboxylic acid derivatives, then end the lecture for today. In the next video, we're going to look at the mechanism on how these derivatives are synthesized. Let's look at this carefully. Carboxylic acid derivatives, as the name implies, derivatives. So derivatives means that they are derived from carboxylic acids. So every compound that can be derived from carboxylic acid is called a carboxylic acid derivative. Known ones are acid halides, in which the halide here can be of the halogens, being it chlorine, fluorine, or bromine. We have acid anhydrides, we have esters, we have amides, we have thioesters, and acyl phosphates. All these compounds can be derived from carboxylic acids, therefore we call them carboxylic acid derivatives. They are derivatives because they can be derived from carboxylic acid. Here you can see that the OH here of the carboxylic acid has been replaced by the halogen here. Here it has been replaced by a carboxylate system. Here is a coazide system. Here is an amine system. Here is a thiol group and a phosphate group. Because all these ones are used to replace carboxylic acid, we say they are derived from carboxylic acids, and therefore they are called carboxylic acid derivatives. Few ways of synthesizing them include what if you have carboxylic acid here and you add a thionyl chloride here. Thionyl chloride in a base are going to form an acyl chloride. Carboxylic acid plus another carboxylic acid will give you an acid anhydride. Carboxylic acid in an alkaline, or let's say acidic solution of alcohol, will give you an ester. Carboxylic acid with an amine will give you an amide. Then a carboxylic acid with a base will give you a carboxylate ion. Just another scheme. We have a carboxylic acid, then you add a thionyl chloride. It is going to give you an acid chloride. So this is the reagent for synthesizing acid chloride from carboxylic acid. We have a thiol compound here plus carboxylic acid giving us thioester. We have an amine here. This is an amine. This is a thiol group. This is a thionyl chloride. We have a carboxylic acid plus another carboxylic acid in heat, or a carboxylic acid with an acyl chloride. We are going to get an acid chloride. A carboxylic acid with an alcohol, you are going to get an ester, and a carboxylic acid with a base will give you a carboxylate ion. All these compounds are synthesized through a mechanism we call a nucleophilic addition elimination mechanism. So in the next video, we are going to look at the mechanism behind the synthesis of all these compounds. Thanks for watching. Don't forget to subscribe so that you can receive every update from this channel. This is Enoch tutorial. Thanks for watching. Bye.